children. I am Shushmita and welcome back to another video. Previously, you have learned about Fleming's left hand and right hand rules. Now, in this video, let us gather some information on electric motors, which involve the magnetic effects of electric current, and electric generator, which involves the electric effects of moving magnets. Learning outcomes. At the end of this session, you will be able to understand about electric motor, electromagnetic induction, Faraday's law, electric generator. Keywords. Electric motor, a device that converts electrical energy into mechanical energy. Magnetic field. Commutator, a device that reverses the direction of flow of current through a circuit. Electromagnetic induction, the process by which a changing magnetic field in a conductor induces a current in another conductor. Electric generator, a device which converts mechanical energy into electrical energy. Before starting this session, let us look at the concept map of today's session. An electric motor is a rotating device that converts electrical energy into mechanical energy. The electric motor is used as an important component in electric fans, refrigerators, mixer, washing machines, computers, MP3 players, etc. We have already seen that when an electric current is passed through a conductor placed normally in a magnetic field, a force acts on the conductor and this force makes the conductor move. To understand how a motor works, we need to understand how a current carrying coil experiences a turning effect when placed inside a permanent magnetic field. Consider a rectangular coil ABCD of insulated copper wire. The coil is placed between the two poles of a magnetic field such that the arm AB and CD are perpendicular to the direction of the magnetic field. The ends of the coil are connected to the two halves P and Q of a split ring. The inner side of these halves are insulated and attached to an axle. The external conducting edges of P and Q touch two conducting stationary brushes X and Y respectively. Current in the coil ABCD enters from the source battery through conducting brush X and flows back to the battery through brush Y. The current in arm AB of the coil flows from A to B. In arm CD, it flows from C to D, that is opposite to the direction of current through arm AB. On applying Fleming's left hand rule for the direction of the force on a current carrying conductor in a magnetic field, we find that the force acting on arm AB pushes it downwards while the force acting on arm CD pushes it upwards. Thus, the coil and the axle O, mounted free to turn about an axis, rotate anticlockwise. At half rotation, Q makes contact with brush X and P with brush Y. Therefore, the current in the coil gets reversed and flows along the path DCBA. A device that reverses the direction of flow of current through a circuit is called a commutator. In electric motors, the split ring acts as a commutator. The reversal of current also reverses the direction of force acting on the two arms AB and CD. Thus, the arm AB of the coil that was earlier pushed down is now pushed up, and the arm CD that was previously pushed up is now pushed down. Therefore, the coil and the axle rotate half a turn more in the same direction. The reversing of the current is repeated at each half rotation, giving rise to a continuous rotation of the coil and the axle. We have studied that when a current carrying conductor is placed in a magnetic field, it experiences a force. This force causes the conductor to move. Now, let us imagine a situation in which a magnetic field is changing around a fixed conductor. This was first studied by English physicist Michael Faraday. In 1831, Faraday made an important breakthrough by discovering how a moving magnet could be used to generate electric currents. To understand this concept, let us conduct an activity. Take a coil of wire AB having a large number of turns. Connect the ends of the coil to a galvanometer. Take a strong bar magnet and move its north pole towards the end B of the coil. There is a deflection in the needle of the galvanometer to the right. This indicates the presence of a current in the coil AB. The deflection becomes zero the moment the motion of the magnet stops. Now, we draw the north pole of the magnet away from the coil. The galvanometer is deflected toward the left, showing that the current is now set up in the direction opposite to the first. If you move the south pole of the magnet towards the end B of the coil, the deflection in the galvanometer will just be opposite to the previous case. When the coil and the magnet are both stationary, there is no deflection in the galvanometer. It is clear from this activity that the motion of magnet with respect to the coil produces an induced potential difference, which set up an induced electric current in the circuit. The process by which a changing magnetic field in a conductor induces a current in another conductor is called electromagnetic induction. Based on the phenomenon of electromagnetic induction, the experiment studied above generate induced current which is usually very small. This principle is also employed to produce large current for use in homes and industry. In an electric generator, Mechanical energy is used to rotate a conductor in a magnetic field to produce electricity. An alternating current AC generator consists of a rotating rectangular coil ABCD called armature placed between the two poles of a permanent magnet. The two ends of this coil are connected to slip rings R1 and R2. The inner side of these rings are insulated. Two conducting stationary brushes B1 and B2 are kept separately on the rings R1 and R2 respectively. The two rings R1 and R2 are internally attached to an axle. The axle may be mechanically rotated from outside to rotate the coil inside the magnetic field. The outer ends of the two brushes are connected to the external circuit. When the coil is rotated, the magnetic flux linked with the coil changes. This change in magnetic flux will lead to the generation of induced current. The direction of the induced current, as given by Fleming's right-hand rule, is along the direction of A, B, C, D in the coil, and in the outer circuit it flows from B2 to B1. During the second half of rotation, the direction of the current is along the direction of D, C, BA in the coil, and in the outer circuit it flows from B1 to B2. As the rotation of the coil continues, the induced current in the external circuit changes its direction for every half a rotation of the coil. Such a current which changes direction after equal intervals of time is called an alternating current AC. This device is called an AC generator. To get a direct current DC, a split ring type commutator must be used. With this arrangement, one brush is always in contact with the arm, moving up in the field, while the other is in contact with the arm moving down. Thus, a unidirectional current is produced. The generator is thus called a DC generator. The difference between the direct and alternating current is that the direct current always flows in one direction, whereas the alternating current reverses its direction periodically. Points to remember. An electric motor is a rotating device that converts electrical energy to mechanical energy. The process by which a changing magnetic field in a conductor induces a current in another conductor is called electromagnetic induction. An electric generator is a device that converts mechanical energy into electrical energy. An electric generator works on the basis of electromagnetic induction.